In late 1947, a Boeing B-17G Flying Fortress, serial 44-83790, was operating under U.S. military records that place it with the 1377 base unit at Westover, after the U.S. Air Force had already become a separate service. The heavy bomber was flying from Greenland toward Goose Bay when the personnel aboard lost their way, and the aircraft was forced into a fuel emergency over the remote Labrador interior. The emergency was driven by a critical shortage of fuel, leaving the pilots with little or no usable power and forcing them to manage the aircraft as a descending, largely unpowered mass. 9 personnel were on board the aircraft. The mission objective was no longer reaching a designated runway, but rather bleeding off altitude and airspeed in a highly controlled, irreversible descent toward the absolute safest terrain available. At that point, the flight limit was no longer tactical, it was geometric. When a multi-engine heavy bomber loses all mechanical thrust, the pilot is immediately restricted by a rigid energy geometry. Any correction that demanded new thrust was gone, so altitude became the flight crew's only remaining currency. The pilots must carefully exchange their vertical height for forward distance, selecting a landing zone strictly defined by their unpowered sink rate and maximum glide ratio. The trade-off at this boundary is absolute. The pilot must accept the terrain directly along their forward glide path, because attempting aggressive banks or turns to reach a more favorable location risks bleeding off too much airspeed and inducing an unrecoverable aerodynamic stall. Faced with this immovable constraint, the pilot evaluated the surrounding landscape and selected the frozen, flat surface of Dyke Lake as their only viable option. The flight crew committed to the ice field and executed a disciplined wheels-up ditching procedure. By intentionally keeping the landing gear retracted, the pilot reduced the chance that the wheels or struts would dig into the uneven frozen surface. Deploying the gear in this environment could have created a massive snag hazard, grabbing the ice, twisting the airframe, or driving the bomber into a violent forward flip. Instead, the broad lower fuselage of the bomber acted as an improvised ski. The aircraft slid across the hardened ice, continuously dissipating its forward kinetic energy through sheer physical friction along the belly skin. The engineering of the lower bulkheads and subframes held firm against the abrasive load, preventing the fuselage from buckling inward or crushing the crew compartments. Because of this disciplined energy management under extreme operational pressure, all 9 personnel survived the controlled crash without any casualties. The aircraft had safely delivered its crew to the ground, but the large machine was now permanently stranded in a severely unforgiving Arctic environment. On the winter ice, military attention shifted from the rescued crew to the abandoned aircraft. The ditched B-17 still represented U.S. military property, with equipment and instruments that could not simply be treated as ordinary scrap in the open wilderness. Shortly after the initial crash, specialized United States Army Air Force recovery personnel arrived at the resting site directly on the frozen lake surface. Their mandate was strict hardware salvage, but they faced severe logistical constraints while operating on the ice. What happened to the forward fuselage after abandonment is less certain in the public record. Later recovery photographs and accounts note that the nose section was missing and the cockpit area was badly damaged, but they do not securely establish a step-by-step military cutting operation at the crash site. Whatever equipment had been removed, the larger aluminum shell was left behind on the ice, and the military file effectively ended with a wreck that future investigators would have to relocate after the seasons erased the obvious surface evidence. The heavy bomber rested on the frozen surface of Dyke Lake, but this static position represented a strictly limited time window governed entirely by the shifting seasons. When the spring thaw of 1948 arrived, the solid structural support beneath the aircraft rapidly degraded. The thick winter ice layer began to fracture, transition into slush, and ultimately melt, initiating a drastic environmental state change. The large airframe, no longer supported by a rigid surface crust, broke through the thawing ice and sank, introducing a displacement problem that later search teams would have to solve. During that transition, the wreck absorbed ice movement, thawing loads, and lakebed impact. The known nose loss and cockpit crushing can be assigned only to this broader damage history, not to a confirmed step-by-step cause. The stripped bomber descended through the water column and settled onto the freshwater lakebed, later reported at about 23 feet deep. Once resting on the bottom sediment, the physical degradation of the airframe slowed dramatically, but it did not stop completely. For the next 56 to 57 years, the aircraft remained isolated from ordinary human access. The shallow depth hid the wreck from casual aerial observation while placing it in a cold, freshwater setting. Later summer recovery measurements recorded 55 degrees Fahrenheit, with much lower temperatures through most of the year. Those conditions acted as a strong preservation buffer, not an absolute corrosion inhibitor. When a standard aluminum airframe sinks into saltwater or polluted industrial runoff, conductivity, trapped moisture, and contaminants can accelerate galvanic corrosion and chemical oxidation. Dyke Lake offered a much gentler setting: cold, clear freshwater, no ultraviolet exposure at the lake bed, and far fewer industrial contaminants. Those conditions greatly slowed the standard breakdown processes. This environmental preservation created a highly unusual forensic condition. Instead of dissolving into a fragile debris field, the airframe survived in remarkably good condition for a submerged aircraft. The later recovery team still had to treat it as aged structure, not frozen time, extending that caution to rubber, seals, tires, and other non-metallic components that survive better in cold freshwater than they would under sun, salt, and repeated drying cycles. The preserved condition of the structure created a new operational boundary for future recovery teams. Survey work could establish the target, but it could not authorize contact. The investigators now faced a severe administrative barrier regarding who held jurisdiction over the submerged structure. That authority question would control the next phase. In 1998, an investigative search team mobilized to locate the missing heavy bomber, using the official coordinate data recorded by the military decades prior. However, the historical record contained a severe geographical discrepancy. The actual resting site was miles away from the expected location, with later accounts reporting a substantial displacement from the original search area. The search team bypassed that contradiction through local knowledge, repeated search work, and underwater survey rather than a single clean clue on shore. The aircraft was eventually located in July 1998, giving investigators a confirmed submerged target instead of a disputed map point. Locating the structure did not lead to an immediate extraction operation. Instead, the discovery triggered a massive operational freeze dictated entirely by administrative law. The recovery sponsor and Canadian authorities entered a prolonged conflict over legal definitions, ownership, export permission, and salvage rights. The aircraft sat at the boundary between an abandoned historic military wreck, a recoverable object under maritime law, and property whose title still had to be handled through the Canadian Receiver of Wrecks. The project funders argued for a legal path that would allow recovery and preservation, while government authorities retained control over whether the aircraft could be removed from the country. This intense jurisdictional conflict paralyzed the recovery operation for 6 complete years. Only after the legal process resolved enough of that blockade, and after the necessary government approvals were in place, could the recovery team proceed with a physical intervention. With the legal boundary finally resolved, the engineering team immediately faced a severe logistical constraint. Extracting the heavy aircraft from a remote wilderness lake required dismantling the large main wing sections while the structure remained underwater. The rugged terrain and lack of infrastructure ruled out heavy hydraulic extraction equipment or large underwater power tools, so the separation plan had to rely on simple methods divers could execute at the wing joints. Before deploying a dive team to the remote area, the recovery director used intact, dry B-17 airframes, including examples and expertise associated with the Museum of Flight and Goshawk, to reverse engineer the pin extraction sequence. The wings were secured to the center fuselage by large, tightly fitted pins and fittings built to carry flight loads, so the lakebed work had to be solved before the divers entered the water. By rehearsing the sequence of access points, tool angles, and force paths on dry structure, the team mapped the geometry of the tight joint assemblies before the cold water operation began. This dry run reduced the amount of bottom time the divers would spend solving the problem in real time and increased the chance that the wing sections could be separated without unnecessary damage. After that preparation, the next limit was transport: how to capture a massive aerodynamic structure and move it through miles of open water once the primary pins came free. Extracting the strip bomber from the remote lakebed imposed a severe geometry limit on the recovery engineers. Because the dive team was strictly limited to using basic manual hand tools during the underwater disassembly sequence, they could not rely on heavy hydraulic machinery to manipulate or support the massive structural weight. The team had to design a highly specific mechanical lift system to safely elevate the fully assembled center section and the heavy wings off the bottom sediment without inducing fatal stress fractures. Operating in the cold, freshwater environment, the divers successfully executed the complex manual pin extraction sequence, driving out the primary joint fasteners exactly as they had rehearsed. With the structural connections properly mapped and prepared, the heavy airframe was finally ready to be lifted. To safely float the massive structure, the recovery crew deployed 8 professional salvage lift bags. Contemporary reporting described each bag as capable of lifting about 8,000 pounds, while the salvaged aircraft weighed roughly 32,000 pounds. The decisive constraint was load distribution. The bags were arranged as a cradle under the aircraft, so the upward force would be spread across stronger parts of the airframe rather than concentrated at one destructive point. As the divers introduced air into the system, the goal was to free the bomber from the lake bed under even predictable buoyancy. The fully inflated system provided enough controlled buoyancy to float the 32,000-pound airframe into a stable hover just below the surface. However, elevating the aircraft was only the first phase of the logistical extraction plan. The extreme geographical remoteness of the wilderness crash site meant there was absolutely no heavy crane access, road network, or usable industrial infrastructure available on the immediate shoreline. The only viable extraction zone capable of supporting heavy transport trucks was located at a completely different access point on the large lake system. To bypass this rigid wilderness access limit, the recovery directors initiated a complex, neutrally buoyant tow sequence. The dive team secured heavy tow lines directly to the strongest primary fuselage anchor points, connecting the floating wreck to local surface boats. Moving a massive aerodynamic structure through a dense liquid medium requires suspending it safely off the bottom while strictly restricting the forward tow speed. Because the wide wings and broad aluminum fuselage panels of the heavy bomber were originally designed to move through thin air, dragging them horizontally through dense water generated massive hydrodynamic drag. If the surface vessels accelerated too quickly, the sheer resistance of the water column would easily tear the weakened wing joints apart, collapse the remaining structural doors, or shear off the fragile aluminum skin panels. The recovery operators were forced into a strict speed trade-off, moving the suspended wreck at a very slow, highly controlled pace. Contemporary accounts reported that the aircraft was towed through the water roughly 60 to 68 miles to reach usable road access. This methodical subsurface transport brought the airframe to the point where overland movement became possible. The surface vessels guided the massive aluminum cradle through the final miles without breaking any critical structural load paths. At the shoreline extraction point, the wreck was finally positioned for a vertical lift out of the lake. The long underwater transport sequence had completely bypassed the severe terrain limits. The tow had ended. The lift itself would start a different preservation problem. When the bomber broke the surface in 2004, the protected lake bed chemistry ended. The team successfully hoisted the waterlogged airframe vertically onto the remote extraction dock using heavy industrial crane equipment. However, simply placing the heavy hardware on dry land did not secure the survival of the historical artifact. The structural stability of the salvaged metal was suddenly threatened not by mechanical stress or handling damage, but by a rapid biological transition. During its 56 to 57 years on the lake bed, the bomber accumulated biological growth, silt, and residue that were harmless underwater but dangerous once exposed to air. As that coating dried, it could trap moisture and contaminants against seams, rivets, and lap joints, then harden into the damp, dirty surface condition that corrosion control manuals warn against. The recovery crew recognized this immediate surface hazard. To halt the onset of rapid atmospheric oxidation, the engineering team executed a comprehensive post-lift wash. Rather than immediately disassembling the structure or loading the massive pieces onto heavy transport trucks to clear the extraction zone, they intentionally delayed the logistical breakdown process to prioritize material stabilization. The operators deployed high-pressure water hoses to methodically blast away decades of accumulated marine growth from every exposed inch of the fuselage, the inboard engine nacelles, and the heavy wing structures. This high-volume washing procedure had to be completed immediately before the mud and biological matter could harden into a rigid, impenetrable crust. The engineers had to carefully direct the high-pressure streams around the intricate, overlapping aluminum seams, the thousands of structural rivets, and the open structural frames where the military had cut the nose away decades prior. Removing the wet, organic layer eliminated a direct source of trapped moisture and residue at the metal surface. That bought the restoration team time for drying, inspection, disassembly, and longer-term preservation work. With the dockside wash complete, the crew carefully dismantled the aluminum sections and loaded them onto long-haul transport trucks for the overland journey back to civilization. Now the question moved from recovery logistics to flight worthiness. The heavy structural pieces were secured for evaluation, and the next question moved from recovery to airworthiness. Reintegrating a major salvage component from a submerged artifact into an active flight envelope imposes a severe structural constraint on restoration engineers. Surface preservation was only the starting point. Flight use required proof of internal integrity and a zero-tolerance threshold for fatigue. When the dismantled sections of the salvaged bomber arrived at the restoration facility, the engineering team faced an absolute mechanical limit regarding the left inner wing panel from the Dyke Lake B-17. The inner wing panel is a critical load-bearing structure that connects the outboard wing structure to the center fuselage and carries major engine, wing, and flight loads. During flight operations, this zone absorbs continuous shear loads, structural flexing, and vibration. That made inspection a hard gate before any rebuild for flight use. To answer that inspection gate, the restoration team moved beyond exterior review and into a highly invasive component grafting procedure. The mechanics drilled out the original securing rivets and removed the outer aluminum skin, exposing the deep interior architecture and the central spar tubes. The spar tubes form the wing's primary load path, carrying the aircraft's weight in flight. Once the raw structural core was entirely exposed, the engineering team subjected the bare metal to an exhaustive series of non-destructive testing protocols. They scanned the metal for microscopic stress fractures, deep material fatigue, or hidden internal pitting that might have occurred during its long isolation in the wilderness lake environment. The forensic results strongly supported the quality of the preservation environment. After disassembly down to the basic spar tubes, the inspected metal was reported to be in very good shape, with no cracks and no bad corrosion found in the critical spar tubes. That did not make the part new, but it established a verified basis for continued restoration. The restoration engineers then rebuilt the left inner wing panel for possible installation in the separate B-17 known as the Liberty Bell. The historical metal was no longer only a static artifact. It was entering a restoration program governed by modern inspection, documentation, and airworthiness discipline. This validation extended the physical legacy of the recovery, but it did not close it. The Dyke Lake component had moved from lakebed artifact to candidate structure inside the Liberty Bell rebuild. Its next test was the slow, unforgiving discipline of restoration engineering. If the fully restored bomber one day takes off carrying this rebuilt inner wing section, the final question will be how long historically salvaged aluminum can be safely maintained under flight loads.